Hey, welcome back. I'm just checking in on YouTube stream, make sure we have audio, video. Looks like excellent connection is just starting up. And here we go. Seems like things are moving along smoothly. So we had last week on Thursday, Friday, they were working on NanoHub updates. So we lost 2 days of some computational time. Sorry about that. Hopefully you made the most out of like using the learning coaches and sort of getting a chance to review the readings. And I'm just pulling up our kind of calendar of things coming up because this is our last week together. So the course is ending. I said project 5 was due July 4th. You don't have to turn it like July. I should just change this, right? Let's just change this to like July 5th or the 6th, like that. Because I don't want you working on July 4th or yeah, and the weekend. I mean, we're trying to wrap things up. But what I wanted to say about these like last few assignments is we lost like 2 days, which is a significant portion of our time to work together because the server was down. So if you get graded on the modules 1 through 4 and you're not happy with the assessment that I have based on the work, then you can email me after the class and either submit these extra credit module 5 works or resubmit. Oh, why did I do that? Coming back down here because we're down here in July. So hopefully by now you're either working on or done with homework 4 and the reading coach for module 4, the reading assignment, and then working on this project number 4, which is the last required project for the class. And then after that, if this is material that you like and you just want to get some more practice, then definitely take a look at module 5. It combines a lot of the stuff that we talked about in module 4, where we're doing linear algebra, but then also a lot of module 3 work where you're dealing with differential equations. So module 5 is all about taking those differential equations that we worked on, turning them into linear algebra equations, which might seem kind of weird at first, but there's a whole process to the finite difference method. We use different integration methods, which are technically like finite difference kind of methods, but you can do, rather than integrating over time, you can look at it over space too. Okay, cool. So that's the logistics updates for today, is that we're here and oh, actually one more logistical update. Let's switch over to student preview. Because I just opened up the final semester participation assessment. Normally I have a mid-semester one, but I didn't want to overload assessment kind of work because we were already doing all those learning assignments, and I got a sense of like how you're interacting with learning material that way. This is your chance to give yourself your own grade in the class for participation. So it's 20% of the grade, and you can either say that you have actively participated and give me some reasons why, like so like when you were stuck, who were you asking for help? Like how did you reach out? What worked well? Like what were the ways? And here, like either the participation worked really well for you or something else. But anyway, this is the main, and yeah, those are required. This is the main participation final grade for that 20% of the class. So if we come in here and look at our syllabus, we can come down to grading and, oh, sorry, 30%. So 30% of your grade is based on, and I'll I'll apply some of the work that you did towards the reading assessment into this participation grade as well. So make sure you're doing those learning coach assignments. And then I'll put like 20% of your own grade in there that you decide. Cool. All right, so that's our logistics for the day. And now let's jump into some linear algebra work based on my first impressions of returning this homework, and also some places where I thought we could use a little extra explanation here. So let's try. Where do I want to start? I mean, the first problem, let's just do the first problem first. Since we have both the system of equations and we have the matrix here, now we can see how this set of equations turns into a matrix, a vector, and a vector. And so we have all these left-hand side things, all these right-hand side things, kind of left and right of that equal sign, and we can take it all and split it up into coefficients that we know, and then outputs that we're trying to calculate that we also know, and then all these unknown inputs, x1, 2, 3, 4, and 5. So in this case, it's the positions of springs these plungers, 1, 2, 3, 4, and 5. In the first case, we're applying two forces equal and opposite, so it's in equilibrium. There's no question about is this problem solvable? It is a very solvable problem. And an even simpler case might even be let's pop this up. Even simpler, we could say this. This is x1, this is x2, and that's k. I'm going to push on both sides with equal and opposite forces. And if this is the case, then I know the spring has to compress. So x1 is going to be equal to negative x2. So if I look at just this first part, I have a positive f minus a k times x1 minus x2. So if x1 moves to the right, and all that is equal to 0, that's my first part. The second is that I have a negative f with a positive k times that x1 minus x2, and all that is equal to 0. So if I turn this into a matrix format, I want to take the known things, put them on one side, and all the unknown variables, leave them on the other side. So I'll have an f and a negative f is a negative k x1 plus k x2, and then this one is going to be a positive k x1 minus k x2. And I'm kind of walking through this step by step because I thought it might help to see it again. And then what I'll also do is throw this into AI and see if it'll do the same kind of breakdown for us. But anyway, I wanted to show you kind of the old school method because this is thinking through the process of how do I take these equations, these equilibrium equations, and turn them into a series of matrix operations that I can solve. Because once I can turn it into a matrix, then it's easy for the computer to solve it. And this module is all about learning about how the computer does that. But for the most part, if we just say hey, solve this series of equations, we'll get an answer. And linear algebra problems they've been optimized and and sped up. Like there's all sorts of great things, great tools that we can use if it's a linear algebra problem. Okay, so I have these, but even so, the problem that we run into even with this problem is that if I'm trying to solve for x1 and x2 and there's no constraint on what they can be, then if I take equation 1 and add it to equation 2, f minus f is 0, and then a negative k plus a k is a 0 times x1 minus x2. So I just end up with 0 equals 0. And for the most part, that's what happens in all these, whenever we have like this ill-conditioned or determinant of 0 kind of case. In this first case, it's always the same problem. It's not that there's no solution, it's just that there are infinite number of solutions. Because I could say, let x equal 1. And if that's the case, then I could say, and let's say like f and k are both 1, right? If those are known values, equals 1, equals 1, equals 1. So if that would be a 1 minus 1 plus x2. So x2 equals 0. In that case, all right, that's fine. But I could also say x1 equals 2. So then I would have a 1 minus 2 plus x2. So x2 equals, and let's see, equals 1. It's like, okay, then that also works. And really for any value of x1, I can solve for a value of x2 because I have two dependent equations. And really the way that you can kind of see that is like once these two have compressed, let's do this. Once they have compressed, I can take this and slide it left or right by any amount, by 100 meters or 1 meter or 300 meters. The delta x, like how much it compresses, that's one number. But the amount that the actual values of x1 and x2, those are going to keep changing. This is very common, like especially so when we look at this finite element project, we'll take a look at what the condition number of the entire stiffness matrix is. And it's a really high condition number. It's not infinite. It's not infinite. Like it doesn't have a determinant of 0, but it's pretty darn close. Like it's almost an invertible stiffness until we start adding these boundary conditions, because it's the same problem. When you apply a force, even if the forces all add up to sum of the forces is 0, you still have an infinite number of solutions. So again, it's not that there's no solution, it's that there's an infinite number. You can choose any solution as long as it kind of matches these equations. Okay, so we got that. And I'll show you the way that I kind of like to do these things. So let's say my k vector, excuse me, and what do we want to do? So k is going to be equal to 1 and then force is 1. So np dot 1s of 5. Let's do this. N equals 5. And I'm just showing you one step at a time here. If I say NumPy, make me a diagonal matrix with ones, with 5 ones in it. It gives me a 5 by 5 matrix with, well, 2 times ones. So 2 times a vector of ones with 5 2s along that diagonal. So I can add to that, we'll subtract from it, np.ones of n minus 1. And I want to turn that into a diagonal element along the first off diagonal. So now I get 2s, I get 5 2s along here. Then I'm taking n minus 1, subtracting those along there. And I'll do it one more time on that off diagonal below for that -1. And now I end up with this 5 by 5 matrix that matches this one. So now I've made these diagonal elements all the same because that's what it does. So I want to correct the first one. So k00 is equal to 1, k of -1 and -1. That one's also equal to 1. So now when I look at k, I get 1 plus 1 in spots 2, 3, and 4, and the first and the last end up as 1 and 1. And that's what I wanted. Looking good. And then my right-hand side, I'll call it B. And this one, if I want, I could also say it's zeros, since it's mostly zeros, size n, and that way it matches the size up here. It doesn't, I don't get caught up with like, oh, did I plug in 4 values or 5 values? But, and then B of 0 equals 1, B of -1 equals -1. And there I have it. 1 0 0 0 1 -1. So these solving methods in Python, it's linalg.solve. It does a lot of stuff in the background. We dig a little bit into it with this module, with this reading on Gauss elimination, between like Gauss elimination, LU decomposition, and partial pivoting. All those are small elements of what that solve function is doing. So it gives you a little peek under the hood, but that solve method is a lot more advanced than what we're doing here. So it'll fix a lot of problems without you even having to think about it. That also leads to, like, if you have an ill-conditioned matrix because your boundary conditions are messed up, but somehow it seems to work, it'll give you an answer because it's trying to fix it, and it thinks that you might just have like a stiffness problem, like maybe one piece of it is a lot stiffer than the other. So you still need the same kind of problem solving method here of like, all right, check the condition number. Is it singular? Is it ill-conditioned? Otherwise, that solve method will still give you an answer, but you might not be able to trust it. Again, I'm kind of diving like a little deeper into this, just like conceptually to think about this, because that's what I like to do, and I think it's interesting. So if I say solve AB, solve KB, it would help if this one results in an actual like singular matrix error, like it is singular. We might, let's see, could I add, but if it's close to singular, like just due to floating point error, this thing will give me an answer even though the matrix is almost singular. So let's look at linalg.condition of K. This condition number is not like too bad. Let's look at the log of it. So 10 to the 7. It's not terrible. It depends on what answers we're looking for. But the smaller that round off error becomes, oh, so 8, 10 to the 8, 10 to the 9, 10 to the 11. So let's go 3, 4, 5, 6, 10 to the 15. So if it's really close to singular but not quite, linalg.solve is just going to give you an answer. So I've seen cases where people use like random numbers in this, and sometimes they get no error, even though the condition number is very high. Like 10 to the 15 is a very large condition number. Because when we do math, the best we can do is like 10 to the negative 16, our floating point epsilon, machine epsilon error. But anyway, for this assignment, we were just looking at like, hey, it's a singular matrix. But now if I take this same work for case 2, I'm going to make it 4, and I don't need to change that last row, and I don't need to change this last one. But I get a pretty easy to answer question of just like 4, 3, 2, 1. But those are, and if I go back up here, this is a fixed position, so there's only one spring, so it moves 1 unit. Meanwhile, this one has 4 springs along here. It's moving 4 units over. And then if I check the condition number of this new k, I get 29. So 10 to the 1, kind of, or 2.9 times 10 to the 1. So that power there. And that's easy. For a computer, this is very easy to solve. It doesn't need, there's no like tricks that need to happen or anything. It's not doing any pivoting. And the reason for that is that it was the same case as here. Like, all right, well, if it's true for any x1, let's pick an x1 or pick an x2, right? Like we can say, rather than saying that this one equals 1, we could say this one equals 1. And it's the same case here, just picking x5 and saying, like, all right, x5, you're equal to 0. Let's solve for everything else. Another nice way to do it, at least for this case, would be if we said x4 equals negative x2, so they have to move closer to each other, and then x1 equals negative x5, so then we would end up with only these 3. Actually, probably only these 2 because of symmetry. X3 can't move left or right. So we would just have like 2 equations with 2 unknowns. And yeah, that was a long explanation for that one, but I wanted to dig a little deeper because it is kind of important. All right, so now we tried building matrices ourselves. Let's take this LaTeX stuff, come over to our module for Learning Coach or Reading Coach, view the instructions. And open, just taking a while. Come on, open, there we go. I need help with coding this matrix equation. And so what I did was copy and paste the LaTeX code. And the way that I got there was double clicking into that cell so I could actually look at how did these equations get written in a machine readable format. Their LaTeX is okay for humans to read, but it's not great. But it's really nice for AI to read. AI has no problem reading these. So our learning coach recognized that the unknown variables are T1, 2, and 3. I've seen in the past when I've tried this, sometimes it tries to add the input temperature as another unknown variable, but in this case it understood. It separates out these the equations in here. So it divides through by CP, but it doesn't. I mean, I guess it did it okay. It did it fine. So it creates those three equations, it plugs in values, and then it gives us the actual like matrices. I don't trust AI math. I'm trying to see if this one, so 3 over 1 is negative 0.3, but let's see, this one should be 1.2 minus negative 1.2 minus 0.3. Okay, so it does the math okay. These values, I don't know if those are true. So let's do this. Help write the Python code. Oh, it's not giving me the actual. All right, so let's see. I'll copy this code, see if it works. I don't love just like blindly trusting it though, but let's see what happens. The numbers seem okay, and the reason I say that is that the temperature in is 12 degrees, and then we're adding 300 watts of heat to every room. So each temperature has to be more than 12 degrees. Like as it goes through these rooms, it's got to increase in temperature. And it, at least from this diagram, it kind of makes sense. Like if this is feeding in 12 degree air, it's probably the coldest room. And then it gets, for the most part, it goes through room 1 into room 2 and then to room 3. So by the time you get to room 3, it makes sense that 3 Q-ins would have a little bit more, a little higher temperature. So it seems like it's working. But let's double check. I don't love that it just hid the math from us. Show me the Python code, but include the variables so I can change temperatures, mass rates, and specific heat coefficients. And let's try copying this one over. I didn't even look at it yet. I was just going to. And I already imported NumPy. I don't need to input it again. Okay, this is what I wanted to see, was the actual, like, what are the coefficients that I'm dealing with here, and what are the output vectors. And this one, it took that coefficient, that CP, and divided through each term. That's fine. I could have said CP times that array, since it was in all those mass ones. Then I don't have to worry about it over here. But what I want to do is double check print A, print B. So 0.12, 0.02, and what did it tell us? Point 0.12, 0.02, 0.12, 0.14, 0.02. Okay. And then 0.12 and negative 0.12. So it seems like it's working. It was able to do the math reasonably well in this case. But it's something, I never trust AI to do the math correctly. At one point I saw a diagram of like, if you ask AI for A times B, what the result is, and anything that was less than like 7 times 7, it would get right 100% of the time. But this was maybe 2 years ago, that by the time it got to like 7 times 9 or 8 times 11, started getting the answer wrong, that it just didn't have enough data to support the math that it could do there. And so some of the things that helps for this problem is I have all the inputs defined. I have all the equations defined. So when I ask AI to tell me what the matrix set of equations is, it knows exactly where to grab this information, and everything is very well defined. And on top of that, I'm using something that the AI is very good at reading. It has lots of training data to look at LaTeX files and understand equations. It knows that this underscore is not for emphasis, that it's an actual subscript. So if you're trying to take a set of equations and turn it into something that AI can like show you how to turn it into like a matrix and solve it this way, then the best thing to do is like either grab the raw HTML of the tables of like the things that you're trying to do, or the raw like LaTeX stuff, because if I just try to copy and paste all of this, and let's grab this, let's make a new one for this learning coach. I need help solving this problem. All the formatting gets messed up, and it looks like it's kind of grabbing, yeah, this C.P is a little messed up. Let's see if it actually got to, and some of these equations look the same as what we had just found, but most of the time what I've found is that if I try to copy and paste raw, like readable text like this, then things get messed up along the way in that copy paste transition. Cool. All right, and so this Hilbert matrix, coming back to topic of like condition number and this like expected error based on rounding as we start doing math with it. There was a cool example. Someone might have seen like some old videos that I've done on this where we actually looked at like, okay, well, what does this error look like? How does the condition number grow as a size of this thing? So let's say my n is going to be a range from 1 to 21, so 20, so up to but not including that last one. And for Hilbert matrix, I'll show you how we can define, or we could ask. There are built-in functions to create. Show me Python code to build a Hilbert matrix. Oops, I misspelled Hilbert. but it got it. Oh yeah, look at that. And I already imported that. And again, you can import a Hilbert from scipy.linalg. You can import this same function. It'll be a little bit different, but the general idea is that you take the index in this Wikipedia article. If you go here, it's index plus index minus 1, but this is for if we're starting at 1, 1. So 1 plus 1 is 2, minus 1 is 1. But in our case, since we have 0-based indexing, this is 0, 0. So 0 plus 0, that would be a negative 1. So we want to add 1 to that, and then same thing for the rest of these. Just so we can see like a little bit of like what is this thing doing. And so we'll print out that 5 by 5. Looks like it's giving us what we want. And for n in n, let's do this. COND is empty and error is empty. And I'm going to append this linalg.condition of h of n. And then the next thing that I want to do is append the and I've seen people do this in two different ways. One is, let's just take a look at this first. Oh, gotta say Hilbert matrix of n. So here is going from 1 to 21, 1, 20, 500. So this is 10 to the 0. This is 10 to the 1. This is 10 to the 2, kind of 0.5, or 0.5 times 10 to the 3, 5 times 10 to the 2, however, halfway between 10 to the 2, 10 to the 3. Here is 1.5, 10 to the 4. So one way that I could get all of that is take the log base 10 of that. Put one more in there. And now it's 10 to the 0, 10 to the 1, 2, 3, all the way up to 18 is kind of where we max out here. Okay. But what I'm going to do to figure out what that error is, if we check this reading, is coming down here. We're going to check on what condition my condition is in. Matrix norms. The goal is figure out ballpark, like 10 to the negative t, and the condition number is 10 to the c. So 10 to the negative 16, 10 to the c, which is really 10 to the c minus 16. So I could just take the number and multiply them, saying, like, and I'll show you what I mean. And let's do this. We'll just so if I take c times 10 to the negative 16, then I'm taking this 1 I took that 1 times 10 to the negative, or 10 to the 0 minus 10 to the negative 16, end up with 10 to the negative 16. And I'm showing this because I saw a few people using this method of taking the condition number and multiplying it directly with that accuracy number that we have. So I wanted to show this method. It's like, all right, why does that work? And the reason for that is, so we end up with like condition, in that one case, it was 0.5 times 10 to the 3 for that. I think it was a 5 by 5, right? And our error is roughly 1 times 10 to the negative 16. So if I take condition times error, then I get 0.5 times 1 times 10 to the third times 10 to the negative 16, which is equal to 0.5, 10 to the 3 minus 16, or 10 to the negative 13. And yeah, it's a nice way of kind of doing this, taking a little shortcut. Okay, so now we have error and condition for all of these different values. And let's do this. We'll say plt.plot the n comma condition, and it would help to import my plotting. And we'll add something above. And coming back down to this one. And here it's kind of like, okay, so condition number was 0, and then all of a sudden it starts spiking randomly. But what we learned from looking at like errors in module 1 and even convergence in module 3 is that errors, it gets hidden inside of linear plots. So it helps to look at like semilog y so that we can see like, the error was increasing exponentially from 1 to kind of 12 or 13, and then it kind of peters out like something. At this point now we're looking at random fluctuations, and or we could look at, or that one's condition number, but error is basically the same thing, just shifted down by 10 to the 6 by that 16. So we're seeing this, and this is true like even if we went up to like 51, it's gonna bounce around, but we're kind of stuck at this like 10 to the 3, or if we look at our condition number, 10 to the 19. And the reason that it gets stuck there is because like we're still using a math to save and store numbers. So when one thing is like even just creating this Hilbert matrix, at some point like 1 over 52 or 1 over 51 is going to become like diminishingly small. And as I keep trying to do math with it, as I'm trying to like add, subtract, multiply, divide, I just lose a little bit of those floating point operation accuracy. So we're kind of looking at this point, what we're looking at is that concept from module 1, where we're looking at numerical error, and all the way down here where we were looking at truncation error. So it's not the round off error. It's not that we can't approximate a linear set of functions. It's that we literally we don't have enough storage information, at least based on the numbers that we have, 64-bit floating point numbers. We're just looking at random errors kind of accumulating there. Kind of cool, interesting way to like approach this problem, and it solves the same thing that you were asked to do, like show me error, show me condition number. Okay, cool. And then I didn't see this one. This is another one where I saw some people. Let's try this one. I'll write out the matrix just to show you kind of like how I deal with like when I'm trying to input these things. So I like to put every time I make a new row, I add a new line to this array. So a 0, let's do this. SA equals np dot sine of 75 times np dot pi over 180, and CA equals same thing. Oh, I want cosine, so this is CB, and beta is 30, and that's good. And I also want a CA, which is cosine. I'm just saving some variables so I don't have to type out np.sine every time. So sine alpha, a 0, a 1, a 0, and a 0. This first row is this first row. That's what I'm trying to like take this information, plug it in just right here. So then I make my next row, and again, I like to keep them all lined up. Really, the space, if you're inside parentheses like this, the spacing doesn't matter. You can make new lines, you can change the tabs. It's not like when we define like functions and for loops and all that, where the tabs define the beginning and the end. Once you're inside these parentheses, then you're good to go. You can do, it's a little more lenient. So now I have cosine A, 1, cosine A, a 0, 1, and a 0. And the reason I line it up like this is that now I can go back and forth between where I'm writing the code and up here and see that, yes, there should be a 0 below that 1, and there should be a 0 above this one, and then a column of 2 zeros there. So now I get to the next row, a 0, oh, that one's cosine beta over 2. So this should really be divide by 2, like that. Oh, and I need a sine of that too. So now, next line down, I have a 0, cosine beta, a 0, a 0, and a 0. And, you know, like, if I really want these to line up just right, I could start adding spaces there. And again, it doesn't matter. At least this function doesn't care, the array function. And then a negative sine beta, a sine beta, a 0, a 0, and a 0. And again, if I, well, let's do this. Make another row. So this is row 1, 2, 3, 4. 1, 2, 3, 4. My fifth row is now a negative 1, a 0, a cosine alpha, a 0, a 0, a 0. And put a space there. And then the last row is a 0, a 0, sine alpha, a 0, a 0, and a 1. And I do need to close out that last one there. Let's line these up. Cool. So anyway, that's kind of my own bookkeeping trick of like get all the columns lined up the way that they're supposed to be so I can double check are things in line the way that they want. And you can put spaces, you need the commas, but spaces before and after the commas, they're separating values in there. All right, so then B is the final one, is 0, 0. Oh yeah, it would help to actually say that it's an array. And here again, like once you're inside those things, I have a column up here. I might as well define it as a column down here. F times, and actually what I'm going to do is np.sine theta and cosine, sorry, cosine negative np.sine theta, and then a 0 and a 0. And then I'll take that whole thing, let's do it after. And, okay. Oh, theta is not defined. So let's define theta as 45 degrees, np.pi over 4. From scipy dot linalg import lu. And before I do that, let's paste that down there. Let's try grabbing just this Gauss elimination, like the simple Gauss elimination from this reading. So part 2. So coming down, there's some examples, but I'll come down to just where I start doing this Gauss naive. And what this should return is a solution and the resulting like augmented matrix. Okay, coming down here, back to here. So I'll paste that in there, run it. So I run Gauss naive of A and B. And I don't get an error. These big pink boxes, they're telling me that there are warnings, but it continued anyway. So I could just keep going and let bygones be bygones. But the information that it's giving me is not very useful. That the answer is a string of nada numbers, and the augmented matrix is a whole bunch of like nada numbers and infinity numbers. And the reason for that, when I look at this function, is that the very first thing that I do is create a factor, which is whatever element I'm looking inside that augmented matrix, so in here, and divide it by this kk, like the actual like diagonal element factor. My very first diagonal factor is 0. So I'm taking this 0 and dividing it by every number along here in order to solve for how do I get rid of this 1 and this 0 and this -1. So it's causing a problem. And it's like, okay, well, how do I deal with that? The manual kind of simple solution, take this row, turn it into this row. And again, I like to line things up. That's weird. Why did it mess up? There we go. I messed up all my spacing. Oh, I see. So if I switch these two rows, really all I did was say that this is now equation 1 and this is equation 2. it does not change P1 and P2. Those are still the same values. If I start changing the columns, if I want to say like, all right, take this column and switch it with this column, that's full pivoting. So that would change, like P2 would become the first output vector in this case. And yeah, let's do a quick, because this is kind of weird to think about. So let's say I have 1, 2, and 3, 4 times x and y equals 1 and 2. So I just have like a matrix and a vector. I'm trying to solve for x and y. They're in there. If I take these two and switch them, this new matrix is now 3, 4, 1, 2, x, y equals, I do need to switch this side to 1. So it switches that right-hand side, but it does not change the order of x and y, because I'm still saying 3x plus 4y equals 2, which is what this equation said. And then my second equation is saying 1x plus 2y equals 1. So all I did was reorder what that series of equations are. Now let's compare that to, actually let's do this. I'm going to take these columns, switch them with these columns. And I'm not, I'm saying 2x plus 1y equals 1, and 4x plus 3y equals 2. But that can't be right, because these are not equal anymore. So I need to, if I switch these columns, if I'm switching those columns, then I have to say that this output is now y and x. So this becomes a y, that one becomes an x. This is an x, and that one's a y. And then now I have the same equations, but I didn't switch these. I didn't switch like row the right-hand side. So with full pivoting, you have to change what your output vector is, like what you're solving for. But with partial pivoting, you can change the order of the right-hand side and the left-hand side coefficients, and you end up with the same equations without changing this. Normally, you can assume that only partial pivoting is happening, or if partial pivoting is not happening, then it'll get it back the way that it should be. So we only use, in this module, we're only using partial pivoting. So we're only ever switching rows this way. That's a terrible star. And that's what I did here, was switch those two rows. Really, I switched this 0 with that 0, but it didn't really make a difference. And then when I do that, look at this. Perfect answer. So it's not that there was no solution, it's just that I didn't have it set up. I didn't have the equations labeled, like numbered correctly, to actually use Gauss elimination. All right, so now let's take a look at PLU is LU of A. And let's just look at P, L, and U. Yeah, that's okay. I'll leave it this way. So when I use a built-in function to do that LU decomposition, one way to do LU decomposition was what we saw in the readings, was basically Gauss elimination, but you're saving this factor as this L matrix. You like plug it into each of the lower triangular matrices. But in this case, we can plug this in and say like, all right, this is my LU decomposition. There's a pivot matrix, there's the lower diagonal matrix, and then there's this upper. So if I take, so matrix A is kind of this mess of ones and cosines and tangents and all that. If I take L times U, then let's check to see, is it equal to A? And sometimes it's true, sometimes it's false. Because I didn't factor in, this pivot matrix is part of that LU decomposition. So I have to, I think it's just P LU. Oh, P transpose? No, we got to use is close because we're doing some math. All right, so let's get rid of this. All right, so is close. Let's just show a quick little demo. Is close is a great little 1, 2. So if I have like 2 arrays and I want to see like, are they like pretty close? Like, are they basically the same? So like 2.000001 and 2, they're not equal, but darn, they're pretty close. That's what my is close is doing. And if you want to see like more of the options, you can give it like what is the, this would be like a fraction of how close they have to be. Absolute tolerance would be like if I wanted to say, all right, I need to know that it's whatever 2 times 10 to the negative 8 or 1 times 10 to the negative 8 within that absolute. But anyway, and especially with linear algebra, you're doing a lot of like multiplying and adding. Those floating point operations, they add up and they start introducing some error. It's not a lot. It's a lot less than you could ever measure, like for engineers. But so sometimes it's worth doing that is close rather than equal operator. And this is true even for, here, let's try this. Oh, this one. Sometimes you'll get an error. Sometimes you'll get a false when it's an integer versus an array. In this case, or sorry, integer versus floating point number. In this case, it's still working the same way. But anyway, is close is a great little operator. And we'll use it here to say, look, this matrix, if I want to create that original A matrix, I need that P as part of that. So then it becomes the same. So I have my LU decomposition, and let's do a quick time it operation. np.linalg.solve of A, B. And I think, yeah, A and B. And really what I want to do is say x equals that. Solve, and so that took 11 microseconds. All right, so ax equals b. That's a problem that we're trying to solve, but we turned a into p l u x equals b. So I'm going to take this problem, split it up into two problems. So if I take P transpose times P, that becomes identity. So P transpose times B. So L times Y is P transpose times B. And what I did was I turned this whole thing into Y. So U X equals y, so x is my final result. And it seems weird that that's like, why bother doing that? But let's try this little like time it operation. So I'll solve L P transpose B, and then U and Y. So this one is L, comma, oh yeah, lowercase l, P dot T at B, and then X is linalg dot solve of U and Y. It'll take, oh, and for some reason it took longer. It's supposed to be shorter. Let's see, what did I do wrong? (11 microseconds and 24 microseconds. Yeah, it's supposed to be shorter, but I think the solver is getting faster and faster. All right, so let's do this. Copy all this. A is and paste it. I'm going to create like a random 20 by 20 matrix, do PLU decomposition. Oh, and then let's say B RNG dot random of 20. Because it should be faster to solve this two-step process rather than the one-step solve. Let's find out. Drum roll, still twice as long. Interesting. I think because that solver is still treating this as linear algebra. So let's look up SciPy LU factor. So there's LU factor, and then there's LU solve. I'm just trying to grab these two, because now I'm wondering, what am I doing wrong? Why? What is happening, right? All right, so now I need that. All right, so I'll make random numbers. I'm gonna do LU factorization plus that pivot. And then I'm gonna time how long it takes to do that LU solving. So that was 6 microseconds versus 60 microseconds. So this is really, and this LU solver is really taking that lower matrix and the upper matrix and doing the forward and backward substitution. It's probably using like a few extra like speed boosts. So when I was splitting it up into 2 solve methods, it was taking longer because it's kind of analyzing stuff in the background. So there's more background stuff happening here than up in this case, in this like LU solve. So I guess if you're looking for speed boosts and you're using Python, it's better to use this LU factor and LU solve to do this problem, at least if you're looking for those speed boosts. So let's give it a shot. We'll try that. And let's figure out what these LU pivot look like. So LU is lower and upper triangular matrices, and then that pivot, oh weird. Oh, pivot gives you a vector? Oh, I don't know what that pivot is actually. So why is pivot to permutation? That's interesting. So it's pivot indices of a permutation matrix P. It's a little confusing. But then L and U is U and L. So this LU factor is specifically designed to work with LU solve. And LU is a better, like, user-friendly. So I was using LU because then I can actually look at it, but LU solve and LU factor do a good job increasing speed. So if that's our goal, increase the speed, let's give it a shot. So what we need is, now I've got all this extra code, right? So we need this line and the LU solve. So I'll run this, and then print out X and make sure So when I use Gauss naive, I get -1/4 or 1.7 here, -1/4, 1.7, -1, -1.7. So it's giving me the same output. And really what I'm trying to look at is x of 0. And I don't need to redo this factor. Once I factor the lower and upper matrices out of A, it's always the same problem. Like I'm not, when I change the load, this F, like how much it's there, whether it's 1 kilonewton or 100 or 1,000, it's always the same left and right hand sides. So I don't need to redesign that. I can just say times F, where F equals, let's say it's 100 to start. And then that becomes -25. And if it's 1,000, then it's -250, 260, something like that. So if I can do that, I can take all this, say for F in range 100 to 1100, 1101, steps of, I think 10, was it 10 or 100? 10 newtons, that's fine. And I want to grab that thing here, so let's say P1. I'm doing, usually I like to let's initialize it then. We'll just make an empty one. It has gotten faster. It would help if I actually start the for loop with a colon. And now what I can see is exactly what I would expect for a linear set of equations, is that if I multiply my right-hand side by any number, all of the left-hand side, all the variables that I'm solving for will be multiplied by that same factor. So once I have any solution for a linear problem, I actually have every solution, at least in this case, where I'm like scaling that force. And this is true for every linear algebra problem. It doesn't matter how big the matrix is. If you want to know like what happens when the force increases by a factor of 2, your displacements all increase by a factor of 2. Or in this case, it's like that applied force and all the internal forces. They're all directly related to each other. But that was the point of this exercise. It's like, I want you to see that linear algebra is called linear for a reason. Like it's always directly proportional once you have one solution. Getting to this solution can be hard, like solving a 5x5 set of equations ends up with like a 5th order polynomial kind of problem, or like, but once you have the solution, it's always linear. And actually, so the one thing that I'll say about this last part was that some people were creating predictions but not actually plotting data. So data equal, let's import pandas as ed. And so a couple of things can go wrong if you so if I say code equal I think USA, USA. So for USA there is a code, and it tracks down this way. So if I take that, if I take this and say, all right, let me grab the EU and just change the code to, nope, not that, EU. With an empty data set, because there are no cases where code matches EU. There are cases where entity is Europe, and then I can see like, oh, there is no code for Europe. Like Europe is a collection of countries, so I can't actually grab stuff from it. So that was one thing that I noticed, is that some people were getting like not a number kind of fits, and there was, but they hadn't printed out like what information they're actually trying to fit. So that was one thing. The next thing is like, if you're making a fit and you're trying to use it to make a prediction, like always plot the data. You have to plot the data. So I usually plot it before I even try to make a prediction. So I'll plot the year, US, plot the primary energy consumption, make those squares, make these circles, and look at EU. So before I even decide like, hey, I want to fit this data and make a prediction, I always plot it. And then the next step is, all right, well, if that's my plot, where would it make sense to, in this case, draw 2 lines through it? And since they both have the same, their Z matrices are actually the same. And let's do this. So I saw some people using the function ones like. So if this is t, I could say np.ones like that. And then I end up with an array full of ones that has the same structure as t. But another way to do that as a shortcut is t to the 0, and it's the exact same thing, because I'm just plugging it into a function that is always equal to 1. So that's what I like to do. Then the last step is this like t minus my cutoff year. So let's say like year cut off. And this is why plotting the data is so important, because I could look at this and say, all right, maybe 1975. That's when things changed. Year cutoff times, and this is where I'm going to use what's called that Heaviside function, but it's really easy because I'm just saying like t more than that year cutoff, like this. And let's take a look at what that does. I end up with a whole bunch of falses and a whole bunch of trues. So it's true if the year is more than 1975, and it's false if it's not. And how does true and false help us? Well, now I can take this, multiply it in here. A false is a 0, and a true is a 1. So 1975 minus 1975 is 0. 1975 minus 1976 is 1, or 1976 minus 1975. So anyway, that's what I'm doing in there. Now I can use any kind of solution I want. I saw some people using this linalg.lst square. That one works. I like to use solve if I'm just trying to. Oh yeah, and this one. Oh, So I need to add there we go. So right now it's all rows, so really this is Z transpose. So what I want to do is transpose that block so that I get column 1 is the year, column 2 is the year to the 0, column 3 is that heavy side times that T minus that cutoff year. And sure enough, there it is, 1976 minus 1975 is 1. All right, so now I can say np linalg dot solve. I'm going to take Z transpose times Z. That's my left-hand side. And my right-hand side is Z transpose times the US bracket primary energy consumption. Then I get 3 values, 471, negative 91,000, 900,000, and negative 300. Like, all right, well, what does that tell me? Well, I could take this, I could create an array. I could create like a new Z for this, right? So if these are my US coefficients, I could take 3 values, right? NP array of 2025, 1, and 2025 minus 1975, or let's just do year cutoff, at USC. So I'm creating a new Z matrix with the year 2025, multiplying it by my coefficients, and I end up with the prediction is 28,000. Like, okay, is that good? Should it be more? Should it be less? The only, like, at least the first step that I can make is plotting the lines on here to see where they're going. An even better way is I could take this, let's call it T-fit, and I'm just taking all this. Line space 19. Let's go back to 1950 and go up to 2030. I'm going to take my data, plug it in here, and plot my T-fit Did I run this? Oh. So something, oh yeah, that's right. Block of So I have to get the dimensions to match up, same way that I did before. So I'm using that block to create this, and now T-fit and US prediction. Let's do red line, and we'll call this one red squares, and we'll make this one blue circles. So now I can see, I can extend this data I can extend this fit as far as I want. So I'm using this data to create a best fit line before 1975. And then something happens in 1975 and it changes direction this way. That's what that's what this term is saying, that the slope decreased by 300 terawatt hours per year after that point. But maybe I don't like how it fits the second half. Like maybe I think if I was considering like the year 2000, maybe that would be a better number. So I could change this. And there, now things are sometimes better, but also worse. We see still about 200 terawatt hour per year, 230 now. But we're kind of getting rid of a lot of this uptick and that like increase in power here. But the main point that I wanted to make here is like, you need to plot your fit on top of your data to at least make sure that it's capturing some of the data. So in this case, there's a lot of stuff happening that is not on this line, but it does see, if I squint, it does look like the data follows that line a little bit. And maybe this should be back to like 1970. And now looks a little better, right? But now the drop is negative 700 kilowatt hour or terawatt hour per year. Okay, cool. So that was my not so brief linear algebra, some logistical updates for the week, and we only have one more project with our finite element linear algebra project. And then from there, if you want to dive into module 4, you're welcome to. Otherwise, I'll get feedback for you on that last project, and you can revise previous homeworks and all of that. All right, thanks a lot, and I'll see you soon.